Hi, everybody. It's Professor Mitchell. We're continuing today with Chapter 2 on logic and sets. And today we're going to talk about describing sets. The objectives of this section are to understand set language and structure as applied to elementary mathematics, connections between finite sets and whole numbers, and uses of one-to-one correspondence. So here's a famous problem that I'd like you to think about in the back of your mind while we talk about some other things, and then we'll return to this at the end of the video. So the Hotel Infinity problem says that at Hotel Infinity, there are an infinite number of rooms, numbered 1, 2, 3, et cetera, for every natural number n. One night, every room in the hotel is occupied. And here's a cute image I found on Google for Hotel Infinity. My favorite part is no vacancy, come on in. That'll make more sense later. So the first question is, if a guest comes in looking for a room, remember that every room is occupied. If a guest comes in looking for a room, can that guest be accommodated? So think about that. And then the next question, a tour bus pulls in with an infinite number of guests who are all looking for rooms. Can all of those guests be accommodated? All right, so we'll talk about that later. So first, let's talk about sets. So in the years from 1871 through 1884, a mathematician named Cantor created set theory, which has a profound effect on research and mathematical teaching. Sets and relations between sets are a basis for teaching children the concept of a whole number and the concept of less than, as well as addition, subtraction, and multiplication of whole numbers. So when we talk about a set in mathematics, we're talking about any group or collection of objects, and there are all different ways of writing sets. The objects that belong to a set are called the elements or members of the set. So probably the simplest way to identify a set is using what's called roster notation. And that's where you just list the elements inside braces and label the set with a capital letter. So for example, the set consisting of the numbers 1, 2, 3, 4, 5. The simplest way to write that set would probably be what you see here. Some ground rules for sets. Each element of a set is listed only once. No repeats allowed. The order of the elements is unimportant. So that example we were just looking at, 1, 2, 3, 4, 5, that would be the same set as 1, 3, 5, 2, 4. We symbolize that an element belongs to a set using this symbol, which is read is an element of, and we use the same symbol with the little Ghostbuster slash across it to indicate that an element does not belong to a set. A set must be well defined, which means we must be able to tell whether or not an object belongs to the set. So more examples of roster notation. The set C contains the colors red, green, yellow, blue. The set N consists of 1, 2, 3, 4, etc., continuing on in that manner, which is the set of natural numbers. Or the set L, A, B, C, D, etc., the set of all lowercase letters. So the 3 dots that you see at the end of those lists, that's called an ellipsis, and it means that the set continues in the same manner. One thing I want to point out about sets N and L is that L is a finite set, meaning it has a specific number of elements, 26 elements. N is an infinite set, contains an infinite number of elements. So the ellipsis can be used for either kind of set. Then you have what's called set builder notation. So the way that you read this is as follows. This set could be read set C is the set of all elements x such that x is an element of the set of natural numbers and x is less than 5. So this is, to be honest, an overly complicated way in this case of describing the set 1, 2, 3, 4. All right. However, this kind of notation is really useful for more complicated sets. So in this example, we want to use set builder notation to write the following sets whose elements are terms of arithmetic sequences. So first we have the set 2, 4, 6, 8, 10, et cetera, et cetera. In other words, the set of even natural numbers. And actually, you can use that description to write the set builder notation for that set. All right, so they give two possible answers. The first one says the set of all x such that x is an even natural number. And I think that that is a perfectly good answer. The second one is a little bit more mathematical. And what that is the set of all x such that x is equal to 2n for all n element of natural numbers. All right, so that one's a little more complicated, probably a little too complicated for this example. Again, I think the first one works just fine. And then for the second one, it's very similar. You can say the set of all x such that x is an odd natural number. Or if you want to be a little more mathematical, you can say the set of all x such that x is equal to 2n minus 1 for some natural number n. All right. Okay, so now we're going the other way. They're giving me set builder notation and they're asking me to basically convert it to roster notation. So this is the set of all numbers of the form 2k plus 1, where k is equal to either 3, 4, or 5. And so we can find out what the elements of that set are just by plugging in the numbers 3, 4, and 5. If you substitute 3 for k, you get 2 times 3 plus 1, which is 7. If you substitute 4 for k, you get 2 times 4 plus 1, which is 9. And if you substitute 5 for k, you get 2 times 5 plus 1, which is 11. So this turns out to just be the set 7, 9, 11, and I'm not sure why they changed the name of it to A. I just noticed that. We'll just overlook that. All right, the next example, write the set B, which is the set of all x such that x is a positive, even, natural number less than 8. So think about that for a second. A positive, even, natural number less than 8. And you probably don't have to think about it for too long before you figure out that this is just the set 2, 4, 6. All right, definition of equality of sets. Two sets are equal if and only if they contain the same elements. So two sets that contain exactly the same elements are equal sets. Remember that the order of the elements is not important when you write the elements. So if you see two sets that have the same elements but in a different order, those are equal sets. And when set A is equal to set B, we can write A equals B using our ordinary old equal sign. If A equals B, A is contained in set B, and an element of B is contained in set A. In more advanced math classes, we actually use this method to prove that two sets are equal. If A does not equal B, then there must be at least one element that is not contained in both sets A and B. All right, a one-to-one correspondence. If the elements of sets P and S can be paired so that for each element of P, there's exactly one element of S, and for each element of S, there's exactly one element of P, then the two sets P and S are said to be in a one-to-one correspondence. And I think that'll make more sense when you see some examples, like this one here. The set 1, 2, 3 can be placed in a one-to-one correspondence with the set ABC by establishing either one of the following pairings. You could do it like this, you could do it like this, and there are a few other ways also. But either one of those will work. And in fact, we're going to list all of them. One way to illustrate all possible one-to-one correspondences is to use a table, and another is a tree. So using the table looks like this. All right, here are the numbers 1, 2, and 3. And so the rows in the table represent the different correspondences. All right. So you can send 1 to A, 2 to B, 3 to C. You could send 1 to A, 2 to C, 3 to B. You could send 1 to B, 2 to A, 3 to C, et cetera, et cetera. So there are 6 different one-to-one correspondences between those two sets. I think this way might be a little bit simpler. So the way that this works is decide which element you're going to match up with the number 1. So that could be A, B, or C. So let's say that you've chosen A. That means that you have 2 choices for what to pair up with the number 2, either B or C. If you've chosen B, then your only choice for number 3 is C. If you've chosen C, then your only choice for number 3 is B. And you do the same thing for pairing B with 1 or C with 1. And again, you find that there are 6 different one-to-one correspondences. So how can we determine the number of one-to-one correspondences between two sets? In our example, given the element 1 in the first set, there are 3 possible elements in the second set which can be paired with 1, namely A, B, or C. Once we have paired an element with 1, that leaves 2 elements in the second set to pair with the number 2. And then once we paired an element in the second set with 1 and with 2, there's only 1 element left in the second set to pair with 3. All right, so we can answer our question, how many one-to-one correspondences are there between two sets, by using something called the fundamental counting principle. If event M can occur in a certain number of ways, they're calling it little m, put a number there if you want, say 5. If event M can occur in 5 ways, and after it's occurred, event N can occur in, say, 3 ways, then event M followed by event N can occur in 5 times 3, which is 15 ways, all right? And the tired old cliche example that I use for this is, suppose that I'm trying to decide what to wear today, and I've done my laundry, and I have 5 clean shirts and 3 clean pairs of pants. Then I have 5 choices for which shirt to wear. I have 3 choices for which pants to wear. That means there are 15 ways that I can match a shirt with a pair of pants, all right? So the way that applies to our one-to-one correspondences, let's say with 3 elements, you have 3 choices for what to match with the first element, 2 for what to match with the second, 1 to match with the third. That gives you a total of 3 times 2 times 1, which is 6, different one-to-one correspondences. All right, equivalent sets. 2 sets A and B are equivalent, which is written like this with the little squiggle, if and only if there exists a one-to-one correspondence between the sets. Recall that if 2 sets are equal, they have exactly the same elements, which means that equal sets are automatically also equivalent, right? Because you could just match, you know, let's say ABC, ABC, just match A with A, B with B, C with C, okay? However, equivalent sets are not necessarily equal, all right? Remember, all the elements have to be exactly the same. So ABC 1, 2, 3, those are equivalent, but they're not equal because they don't have the same elements. All right, so here we have a few sets. Set A contains the letters P, Q, R, S. Set B contains the letters A, B, C. Set C contains the letters X, Y, Z. And set D contains the letters B, A, C. And they want us to compare all these sets using the terms equal and equivalent. I think this would be a great time for you to pause the video and see how many of those statements you can make. So I'll just do one example to get you started. If I was comparing A and B, I would say that A and B are not equal, and they're also not equivalent. There is no one-to-one correspondence between a set with 4 elements and a set with 3 elements, okay? So again, pause the video and see how many different statements like that you can make. I'd be really, really impressed if you get them all. Okay. We'll compare notes. First of all, did you think of this one? Each set is both equivalent and equal to itself, all right? I wouldn't blame you if you forgot that one. All right. A is equal to A. A is also equivalent to A. Same thing for B, same thing for C, same thing for D. So now to compare different sets, like I said earlier, sets A and B are not equivalent and not equal. Sets A and C are not equivalent and not equal for the exact same reason. Same thing for A and D. However, B and C are equivalent, right? You can easily set up a one-to-one correspondence between ABC and XYZ. However, they are not equal. Same thing for, actually B and D are equal sets, right? ABC and BAC, those are the exact same elements, just listed in a different order. And let's see, did they remember? Yes, sets C and D are equivalent but not equal, just like B and C were. All right, the cardinal number of a set S, denoted N of S, indicates the number of elements in the set S. So as an example, they want to know what is the cardinality of each of the following sets. Some of these are very easy and some of them are a little trickier. All right, so set K pretty clearly, I think, has cardinality 5. There are 5 elements in that set. Set L has cardinality 1. There is 1 element in that set, the number 0. Now the next one is a pretty mathematical example. The set of all x such that x is a real number and x is equal to x plus 1. Well, let's see. Can you think of any number that number is equal to 1 more than that number? Me neither. All right. So the cardinality of this set is 0. That set has no elements in it, okay? And let's see, I don't think I've told you about this yet. Set Y, that is a symbol for the empty set. It is the set that contains no elements. So the cardinality of Y is also 0. X and Y are actually the exact same set. All right, let's come back to finite and infinite sets. A set is finite if its cardinality is 0 or a natural number. So a couple of examples, the set of presidents of the United States and the set of planets in our solar system. Those are both finite numbers. An infinite set is a set that is not finite. All right, you have a concept of what infinite means or infinity, okay? You know, it just basically means something that if you tried to count it, you would eventually have to give up because you don't have enough numbers, right? The set of whole numbers is an example of an infinite set. The set of solutions to the equation x plus 1 equals x plus 1. In algebra, we call an equation like that an identity. No matter what number you plug into it, it's true. So the solution set for that equation is actually all real numbers. All right, the universal set, or universe, denoted U, is the set of all elements being considered in a given discussion. All right, so normally that would have to be specified at the beginning of the discussion. In a math class, a discussion is often a small batch of problems. All right. Suppose the universal set is defined as the set of all x such that x is a member, that's a little typo, of the US Senate. All right. So in case you didn't know, the US Senate has 100 members. Each state gets 2 senators. Every so often there's a vacancy, but usually there are 100. Denote the universal set with a large rectangle, and particular sets are indicated by geometric figures, usually circles or ovals, inside the rectangle. In this case, only members of the US Senate are included in the rectangle. This pictorial representation is called a Venn diagram. So here's the rectangle that represents all US senators. And now we'll consider sets that live inside of that universal set. So for example, consider the members of the universal set U who are female. Since this set is wholly contained in U, but does not contain all the members of U, we denote this set with a circle like this, okay? So there are certain senators that live inside that circle, and there are other senators who live outside that circle. If we wanted to talk about the senators who live outside that circle, we would do it like this. That's called the complement of the set. Consider the members of the universal set U who are not females. This is the set of all members of the set U that are not in set F. We refer to this set as the complement of set F and denote it by the shaded region in the figure below. So you see the green shaded region inside set U, but outside set F. And the way that we write the complement of a set is by putting a bar over the name of the set. So F bar is the set of all X, such that X is a US senator who is not female. All right, so officially the complement of a set A, written A complement, A with the bar over it, is the set of all elements in the universal set U that are not in A. That is, A complement is the set of all X, such that X is an element of U, but not an element of A. All right, so here's an example. If U is just the letters A, B, C, D, so that's our whole universe, just those 4 letters, and B is the letters C and D, let's find B complement, U complement, and empty set complement. All right, it's getting a little weird. The first one's pretty simple though. I think B complement, we're just looking for everything in the universe that's not in B. B contains the letters C and D. That means B complement is going to contain A and B. All right, U complement. Let's see, how would I describe that? That's the set of everything in the universal set that is not in the universal set. Oh, that's nothing, all right? Imagine taking your universal set and throwing out the elements that are in the given set. That'll leave you with your complement. If you throw out everything, you're left with nothing, all right? And then empty set complement. So remember, the empty set is the set that contains nothing. What elements are not in the empty set? Well, all of them, all right? So empty set complement would be the whole entire universal set A, B, C, D. all right? If at times this stuff feels a little, kind of mind-blowing and weird, that is perfectly natural, all right? It does for me too sometimes. All right, next example, this one's a lot simpler. If U is the set of all animals in the zoo, so the set of all X such that X is an animal in the zoo, and S is the set of all X such that X is a snake in the zoo, describe the complement of S. Well, the complement of S would be all the animals in the zoo that are not snakes, all right? Here's another example. If the universal set is natural numbers, and E is the set of even numbers, and O is the set of odd numbers, what are E complement and O complement? Well, I think that one's pretty simple. Within the world of natural numbers, everything that is not even is odd, and everything that's not odd is even, which is why E complement is just O and O complement is just E. Subsets. Set B is a subset of set A, which is written like this. Notice the similarity between this symbol and a less than or equal sign. If and only if every element of B is an element of A, all right? I've always felt that subset is a very simple concept that has a definition that just makes it sound way too complicated, all right? Basically, a subset is a smaller set that lives inside a bigger set, okay? When a set A is not a subset of another set B, then we write it like this: A is not a subset of B. Notice that this definition allows for B to be equal to A. So again, think of less than or equal. This is like the or equal. So what B is a subset of A means, it means that every element of B is also an element of A. And we'll see examples here in a minute. We talked about this, I think, a little while ago. All right, this is when I talked about in more advanced math classes, this is how we prove that two sets are equal. If A is a subset of B and B is also a subset of A, that means that the sets A and B have to be equal. Now, sometimes we want to specify that the two sets are not equal, just one is a subset of the other one. So then we're talking about proper subsets. Suppose set B is a subset of set A, but B is not equal to A. Then there must be at least one element of A that is not in B, and they're indicating that with a point here. We say that B is a proper subset of A, which is written like this. Notice no more or equal underneath, okay? That's called a proper subset. All right, example. Let A be the set 1, 2, 3, 4, 5. B is the set 1 and 3. And then P is this complicated sounding thing, the set of all X such that X is equal to 2 to the power n minus 1, where n is a natural number. And they want us to identify all the subset relationships that occur among these sets. So first, let's figure out what set P is. So if you start plugging in natural numbers, starting with 1, you get 2 to the first power minus 1, which is 1, and 2 to the second power minus 1, which is 3, to the third power minus 1, which is 7, et cetera, et cetera. So P is an infinite set that starts off 1, 3, 7, 15. And I think for this problem, that's about all we need to know. So we can see that B is a subset of A. So remember, a smaller set that lives inside a bigger set. 1 is an element of B, it's also an element of A. 3 is an element of B, it's also an element of A. bam, that means B is a subset of A. And then that's about the only interesting subset example among these. The only other things you can say is that each set is a subset of itself. Okay. All right, using the same example, identify all the proper subset relationships that occur among these sets. Wait a minute, I think they forgot one, didn't they? Yes, they, oh no, they didn't. B is a subset of P, yeah, we got that one. Except I don't think I talked about that one, did I? Yeah, B is a subset of P because look, the numbers 1 and 3 are also in set P. Okay, so I'm sorry, there are two interesting subset relationships in part A of this example. And then for proper subset relationships, well, we could use the same, two interesting ones from part A. B is a proper subset of A. B is also a proper subset of P, okay? But this time we're not going to use A as a subset of A, B is a subset of B, P is a subset of P, because those are not proper subsets. The number of subsets of a finite set. So let's start with a set that has one element, like P, which is the set containing only the letter A. That set has two subsets, the empty set and the whole set. So one thing that I haven't mentioned to you yet is that the empty set is a subset of every set. That sounds like maybe a good topic for the discussion boards. Now let's take an element a set with two elements. That set would have four subsets. Again, the empty set, again, the whole set, and also the set of just A and the set of just B, all right, four subsets. And then if R contains three elements, then R has 8 subsets, the empty set, the whole set, and then there are 3 subsets that have one element, A, B, C, and there are also 3 subsets that have 2 elements, AB, AC, BC. Okay, now this reminds me of the problem we talked about in chapter 1, the danger of conjectures, I think it was called. That was that problem where you put the points on the circle and then draw lines going across and count the number of regions that are formed. That also started out 2, 4, 8, but did not end up following that pattern. Well, I promise you that this time it does. In general, if there are n elements in a set, then there are 2 to the power n subsets of that set. So if my set had 4 elements, A, B, C, D, it would have 16 subsets. Okay. All right, the last thing we'll talk about before we go back to hotel infinity, remember that thing, is inequalities and application of set concepts. So suppose that A and B are finite sets. If A and B are equal, then the cardinality of A and the cardinality of B are equal. In other words, the two sets have the same number of elements, and A and B are also equivalent. It is possible to establish a one-to-one correspondence between A and B. If A is a proper subset of B, then the number of elements in A has to be strictly less than the number of elements in B, and it is not possible to establish a one-to-one correspondence between A and B. However, all of that goes out the window when your sets become infinite. So for example, if you take the set of natural numbers and the set of whole numbers, the only difference between natural numbers and whole numbers is that whole numbers include 0. Other than that, they have exactly the same elements. So the question is, is there a one-to-one correspondence between these two sets? You know, it kind of seems like set of whole numbers is bigger because it has one. I mean, natural numbers are a proper subset of whole numbers, right? Every natural number is a whole number, but the number 0 is a whole number that's not a natural number. So that means that natural numbers are a proper subset of whole numbers. However, it is still possible to establish a one-to-one correspondence between the sets by letting each element in N correspond to a number in W that is 1 smaller. So match the natural number 1 with the whole number 0, match the natural number 2 with the whole number 1, and in general, match the natural number N with the whole number N minus 1. So even though N is a proper subset of W, there is still a one-to-one correspondence between N and W. All right, and because there's a one-to-one correspondence, that means that N and W are equivalent sets. And that brings us back to Hotel Infinity. So remember what the problem said at Hotel Infinity, pictured here. There are an infinite number of rooms, numbered 1, 2, 3, etc., for every natural number N. And one night, every room is occupied. So the first question was, if a guest comes in looking for a room, can that guest be accommodated? So at first you think, nah, every room is occupied. How am I going to fit another person in? Well, that's where it comes in handy that this is Hotel Infinity. Because what you can do is for each natural number N, move the guest in room N to room N plus 1. So you get on the intercom system and you say, ladies and gentlemen, I'm so sorry for the inconvenience, but can you please move to the room that is 1 room number bigger? So if you're in room 1, you move to room 2. If you're in room 2, you move to room 3. If you're in room 29, you move to room 30. And that is going to free up room 1, and then you give the new guest room 1. So then just when you've wrapped your head around that, then I come along and I ask, if a tour bus pulls in with an infinite number of guests who are all looking for rooms, can all those guests be accommodated? And at first you think, I don't see how this is going to work. You know, it's not like I can shift everybody over an infinite number. I mean, I need to be able to tell everybody what, room to move to. Well, this is where you have to think outside the box a little bit. So what you're going to do in this case is for each natural number N, you move the guest in room N to room 2N. So instead of having everybody add 1 to their room number, you have everybody multiply their room number by 2. If you're in room 1, you go to room 2. If you're in room 2, you go to room 4. If you're in room 3, you go to room 6. And so all of the guests that were already here go to an even numbered room. And guess what? That frees up all of the odd numbered rooms for my infinite tour bus. Isn't that fun? So that's one application of one-to-one correspondences. And that's going to do it for this video. We'll see you next time.